This is not a card trick. This is not a card trick. This is not a card trick, only an illusion. When servicing the E3, don't be fooled by illusion.
Hello and welcome to EMU Systems Emulator 3 service video. My name is Tim Swartz and I manage the service department at EMU Systems. In an effort to help you understand and better service the Emulator 3, we have assembled this service video. We have included an E3 overview covering both the E3 standalone and system, disassembly procedures, engineering change orders, calibration, and troubleshooting basics. And now, with no further delay, let's begin. Currently, the Emulator 3 consists of 4 models: the 6080 4 meg rack, the 6082 8 meg rack, the 6081 4 meg keyboard, and the 6083 8 meg keyboard. All models include a date code in the serial number to properly identify the date of manufacture. The date code is read at the front of the serial number. For example, 12-7-100 was built in December of 1987. The 12 stands for December and the 7 stands for the year. 07-8-0600 was built in July of 1988, with 7 standing for July and 8 standing for the year of 88. 038-0300 was built in March of 1988, and so on. When servicing the E3, it is important to know the customer's serial number to help you make better troubleshooting decisions. The Emulator 3 is a complex system and requires a great deal of technical expertise. Understanding the basic operations is essential to diagnose a failure. So at this point, I would like to introduce the Chief Wizard of EMU Systems, Mr. Dave Rossum, to explain the technical overview of the Emulator 3.
Well, this is great. They let me out of the office and gave me something to hit people with as well. This might be fun. The Emulator 3 consists of 5 major circuit boards located in the card cage. Their contents are, number 1, the main computer board, or CPU, which holds an awful lot of what are the functions of the instrument. Then there's a microcontroller board that controls the information that's going out to the sound channels under the direction of the main CPU. There's a separate board for the analog to digital converter. That takes care of the audio coming in when you're sampling, and also any of the real-time controls that have to be converted to numbers for the computer. Finally, there are 2 output channel boards. They each hold 8 channels each, and we had to split it up that way because 16 channels won't fit on one board or even come close. There are a couple other boards in the product. One is an analog output jack board that talks primarily to the 2 output boards and brings your audio out to the outside world on the back panel. And a digital jack board that takes the information from your various digital peripherals, such as MIDI and RS-422, and your SCSI bus, and brings those out. Let's get down to specifics with the CPU board. If we start from where a user would typically start, pressing a button on the front panel, the first thing we run across is the scanner CPU. This is a separate little computer inside and should be pretty familiar to those of you who have worked on Emacs before. It's the same chip with the same program in it, performing basically the same function. The scanner's CPU job is to inform the main CPU whenever a change has happened on the keyboard or front panel, and it does so through a parallel interface on over to the main CPU. Once again, those of you with Emacs experience will find the CPU fairly familiar. It's a 32016 CPU with an associated timing and control unit, similar to the Emacs, except it's a 16-bit version, and it has associated with it a floating point coprocessor, which enables it to do floating point computations very quickly. The CPU has a multiplexed address and data bus. We get the address out of that by simply latching it through a couple of latches, which present a parallel address bus throughout the rest of the instrument. Those of you familiar with computers know that they have to have memory in order to operate. There are 2 major blocks of memory in the Emulator 3. The first is a pair of EPROMs. These hold the program for bootstrapping the instrument, that is reading the main program off of the hard disk or floppy disk. And they also hold some tables and other information used by the instrument during normal operation. The other hunk of memory is dynamic RAM or DRAM. This is read-write memory. It's controlled through a PAL holding the memory control equations. And it holds both the Emulator 3's operating program, which has been loaded off of a disk, and the read-write variables required for operation. Also on the CPU board are a number of peripherals, some fairly simple, such as the timer, which keeps track of when the CPU has to do things and interrupts it through an interrupt latch and interrupt logic, and some more complex, such as the serial chip, which talks via MIDI and RS-422, along with the SIMD interface. This serial chip is a new chip for EMU. It's a serial communications controller. It's also used in a Macintosh. If you're familiar with that computer, it will probably seem familiar. There's a floppy controller, once again identical to that in the Emacs. It's a single chip 1772 controller. And a SCSI controller, which you'll also find very similar to the one in the Emacs. The various peripherals are selected by a handful of chips, which are PALs and decoders, generating the chip selects. These just implement straightforward logic equations and should be fairly simple to follow. A couple other minor peripherals on the CPU board include the LED latch. This just holds on to information for the LEDs and a couple other miscellaneous bits that the computer has to know. And also the input port for a few of the push buttons that don't go through the scanner CPU. The data bus is finally buffered before it's sent out to the other cards in the system, and also from that point follows a cable on up to the main front panel and the liquid crystal display that talks to the user. Moving on now from the CPU board, the first peripheral we'll talk about briefly is the microcontroller. Those of you who have worked on an Emulator 2 are probably familiar with microcontrollers. They're basically special purpose computers that operate very quickly with a very simple program to do a simple operation on a number of channels. In this case, our channels are the Emulator 3 16 sound channels. And the microcontroller board is a complicated circuit, practically impossible to debug by simple oscilloscopes and things like that. The microcontroller board has on it also the dynamic RAM for all of the sound memory. And this is probably what you'll find most commonly you're going to that board to debug. It's a series of SIMs or surface inline modules on that board, fairly obvious when you go to it. The microcontroller talks to the CPU and also to the output boards where it gets requests and sends out acknowledgments to the 16 individual output channels, along with sending the sound data that has been accessed from the sound memory RAM located on this board. From the microcontroller, let's skip on over to the analog to digital converter board. That's a much simpler board, has some fairly straightforward interfaces on it. It talks to the computer in only a few fairly simple ways, one of which is the actual converted data from the analog to digital converter chip. This passes from the chip in a serial line over to a couple of serial to parallel shift register converters and onto the CPU's parallel data bus. The other place the CPU talks is via a data latch that tells the analog to digital converter which signal to convert. That might be one of a number of the real-time controllers, or it might be the audio input channels at two different sample rates. The actual stereo analog to digital converter is a single chip converter. It's the same converter sound found in the Sony PCM F1 and the PCM 501 digital audio converters. If you're familiar with those, you'll probably know this chip. It's a fairly complicated chip to understand. It's running at about 88 megahertz operational frequency and has directly associated with it the sample and holds that grab the analog data in. You'll find some fairly funny waveforms going on in there and some fairly obscure circuitry that's even impossible to understand even if you speak Japanese. Fortunately, it's a single chip. You probably can swap it out if it seems to have failed. Signals for this are generated by a couple of PALs, which are written by the CPU and know what sample rate you're converting at. The data coming into the sample and holds, as I mentioned before, is switched from 3 sources by a couple of analog muxes here. It can come from either a 44.1 kHz channel or a 33 kHz channel from the audio or from the real-time controllers. Getting back into the analog circuitry, we come directly from the sample input jack into a pair of VCAs. We use VCAs here because this signal is terribly noise critical. We don't want to wire it through more wire than is necessary up to the front panel board and pick up digital noise there. The sample input pot directly talks to these VCAs and attenuates the signal there. It's then passed into the anti-aliasing filters, which are a pair of laser-trimmed elliptical filters, and those come into the separate channels which are selected at these analog muxes. That's pretty much it for the ADC board. The last board that we have to talk about is the output board, of which there are 2. Looking at the output board, there's some common circuitry, and then a number of circuits that are very obvious on the board since they're repeated 8 times and the layouts are practically identical between them. The common circuitry does a couple of functions, one of which is supplying the control voltages, the analog control voltages, to the analog processing chip. You'll find for each of the 8 channels on the board 5 control voltages, which are the 2 filter control voltages for frequency and 1 Q control voltage, a gain control voltage, and a pan control voltage. These are created from a number that's given by the CPU and latched on the board to a 12-bit digital analog converter. The CPU also writes, and be careful of this because the actual latch for this is located over in the analog to digital converter board, even though it's logically associated with the output boards. The latch grabs the information to control the sample and holds that will grab this control voltage coming out of the DAC and hold it for a single control voltage for a single channel. So the CPU is constantly refreshing these sample holds and passing the appropriate voltages out to the output channel. The other common circuitry on the output board consists of 3 multiplexer and demultiplexer type of circuits, one of which simply supplies the chip selects to the 8 sample controlling circuits. We call them F chips on the board. The other 2 circuits take the request and acknowledge lines out of the F chip, multiplex them down to single lines to pass back to the microcontroller, which is servicing these F chips. Jumping now into the individual channels, each channel begins with one of these magical F chips. It's actually a fairly simple chip to understand at its most basic form. It's taking the master 20 megahertz clock from the Emulator 3. It's told by the CPU along the data bus what pitch that channel is supposed to be playing at. That information is updated by the CPU as the user changes what information would contribute to the pitch. The F chip then knows when it has to output a new sample. Well before that's required, it sends a request out to the microcontroller saying, hey, I need some data. Sometime later, it's typically somewhere in the neighborhood of 1 to about 8 microseconds later, the microcontroller will get around in its program to answering this particular channel and send back a data acknowledge that says that the sound data on that line represents the sample that's going to be next needed by that F chip. The F chip says thank you to itself, grabs the data, and remembers it for when it needs to be output. The next function is sort of the tricky part of the F chip. It then doubles the sample rate. In other words, if we want to be outputting at 44 kHz, the F chip decides to do everything at 88 kHz, which means that every other sample is going to output the honest data it got from the microcontroller. But those samples in between, it's going to interpolate that data by means of a complex digital filter inside the F chip and give us a second sound data that most likely will be between the surrounding points, but because of the magic of digital filters, you might actually find it outside of the surrounding data points on exceptional circumstances. So the data coming out to the 16-bit DAC every other time will be data from the microcontroller, and the in-between slots will be this fairly mystical DSP number. In both cases, it's grabbed by an analog sample and hold. This circuit is required to deglitch the DAC. That is, when the DAC switches, it gets little spikes on it. If the sample and hold weren't there or were broken, you'd get fuzzy data out of the sample and hold, and you'd hear minor degradation in the audio quality. We come from the output of that sample and hold and go to a single semi-custom analog processing chip that has really 5 functions in it. The first is a simple 3-pole low-pass filter that tracks the pitch information sent to the F-chip and is simply reconstructing that audio data to take out the sharp corners that are put in by the digital sampling process. The next is a familiar 4-pole synthesizer low-pass filter. It gets a cutoff frequency and a cue that are familiar to almost anyone dealing with analog synthesizer technology. This is then passed to a master VCA, which receives a gain control voltage, again very familiar in analog synthesizer terms. That's then passed to a pair of VCAs that get a pan control voltage, creating your left and right audio outputs. Finally, those are passed out to the analog jack board, and there's a little hunk of circuitry on the analog jack board that actually creates the mix output, which is probably what you've been listening to, and passes out to the output world. That's essentially the circuitry on the board, on all the boards in the Emulator 3, and should give you a pretty good picture of, from the front panel, how does it actually go out to creating a sound at the output. Thanks.
Thank you, Dave, and we hope that they let you out of your cage a little more often. We really enjoyed that. In addition to using the Emulator 3 as a standalone device, it can be attached to up to 6 small computer systems interface called SCSI devices. Software version 2.0 or greater is required to operate the system. The system consists of the EMU Systems HD300 hard disk, the EMU Systems RM45 removable hard disk, the Macintosh personal computer, the Macintosh internal hard disk, and a second Emulator 3. When configuring the system, it is critical to select the proper SCSI address for each device to avoid catastrophe. In addition, the total SCSI cable length should not exceed 18 feet. This means that the last device should not be any greater than 18 feet from the first device. This diagram represents one E3 system. It basically consists of the E3 with 2 storage devices. The E3 uses the default of SCSI ID number 0, with the internal hard disk set to ID number 1. When attaching additional storage devices to the E3, they need to be set to SCSI IDs other than 0 or 1 to prevent any conflicts. Both the HD300 and the RM45 have hardware jumper blocks used for setting this address. This is the HD300. It has a 300 megabyte Winchester drive. The SCSI jumper block is configured in a binary fashion. The jumpers are block 1, 2, 3, and 4. When no jumpers are in place, the ID number is 0. When the first position is jumpered, the ID becomes number 1. This is the way internal hard disks are set on the E3 before shipment. This makes the internal drive D1. When the second position is jumpered, the device becomes D2, or ID number 2. This is the configuration both the HD300 and RM45 are set. If both are to be installed on the SCSI bus, one will need to be changed to ID number 3 with the first 2 positions jumpered. In this diagram, we have expanded the system to include the Macintosh personal computer and another E3 with an internal hard disk. As you probably have already guessed, several SCSI IDs will have to be changed to make all the devices talk to each other. With the Macintosh computer in the system, it will conflict with the internal hard disk of the E3 due to the computer's internal hard disk being set to SCSI ID number 1. Also, the E3 internal hard disk needs to be set to SCSI ID number 2. We then set the HD300 to SCSI ID number 3 and the RM45 to SCSI ID number 4. The second E3 is then set to SCSI ID number 5 using the software command located under Master and then Disk Utilities 0. The second E3's internal hard disk jumper block will need to be hardware jumper to ID number 6. The Macintosh computer is factory set to SCSI ID number 7. This configuration will allow all devices to share the same SCSI bus. One point to remember, the total length of the SCSI cabling should not exceed 18 feet. This means that in this setup, cables from device to device should be 3 feet or less. Before you begin, take a formatted E3 floppy disk and save the software using Disk Utilities from the hard disk to a floppy disk. This will save the system's calibrations and trims. If you boot from a floppy disk, on the other hand, the system will boot and use the floppy disk system's trims and calibrations. The system was designed this way so that when somebody boots from their hard disk and then loads copy software from the floppy to the hard disk, they won't overwrite their system calibrations and trims. So remember, before you start, get a copy of the software on a floppy disk, just in case you happen to overwrite the user's software. Make sure you have adequate area to work and that you are properly grounded to avoid static discharge to sensitive components. A static workstation, such as this one, is highly recommended. First, rock the keyboard on its back and remove the 8 screws on the bottom. Now, rock the keyboard back to its original position and remove the 4 screws in the rear. Carefully lift the top chassis up, taking note of the position of the front panel ribbon cable. This is important to note for dressing the cable when reassembling. Be very careful not to damage this cable when lifting the top cover. You now have access to the inside of the keyboard. There is a card retainer that is secured by 1 screw from the top. This will need to be removed to gain access to any of the 5 PCBs. The retainer can be released by applying pressure on the base of the card cage. The card cage is secured by 2 screws to the base. If removal of any of the bottom 3 boards is required, these screws need to be released and the cage tilted upward. Cables will need to be undressed, giving access to the tilting. The card cage houses the microcontroller PCB on top. Next, the CPU PCB. Third down is the ADC PCB. And the bottom 2 boards are the output boards. The bottom output board is output channel 9 through 16, and the next to bottom is output channels 1 through 8. The E3 rack mount is very easy to open. Remove the 6 screws on the top and lift off the cover. The boards can be removed by removing the PCB brace and removing the 1 screw. You can now remove any of the 5 boards. Production of the Emulator 3 began December 1987, 1 year ago. Since that time, we have improved the product in many ways through the process of engineering change orders, or ECOs. When a weakness or flaw in the product is discovered, we first research the alternatives and then come up with a fix. Many of these problems have been discovered by you and brought to our attention, and we encourage that. We want to hear from you when you feel we can make improvements. To identify what ECOs are required, it is important to know the date of manufacture. Once again, this is located at the beginning of the serial number. Units produced between December 1987 and February 1988 require a new method of hard disk mounting. We discovered that the mounting scheme we were using caused slight distortion to the Seagate ST251 frame. One side was mounted to the base, with the other side mounted to the rear of the base. If the base is twisted, the disk drive frame distorts, causing hard disk media errors. In March of 1988, we used this flat steel plate mounted to the base to securely fasten the Seagate drive on a flat surface. This plate works and should not be changed. It was used for 1 month to allow us to ship units while the ideal plate was being manufactured. In April of 1988, we began using this hard disk mounting plate, which secures to the base and back of the base. It is recommended that units not mounted to the flat brass plate be mounted in this manner. Before you begin, back up the hard disk. When a hard disk is remounted to a new plate, it is recommended that it be reformatted with error correction on. Error correction may be turned on in Disk Diagnostics in the Diagnostics menu. After tightening the drive to the plate, the drive may take a slightly new shape and cause the old format not to be read. In September of 1988, we discontinued using the Seagate ST251 and began using the Conner CP340 3.5-inch hard disk. It runs more silent and appears to be more durable due to its isolation from the mounting bracket. It takes a left and right bracket and mounts to the existing standoffs. Just recently we discovered that the Seagate ST251 hard disk digital ground is making contact to the E3 analog chassis ground. This causes digital noise to bleed through the audio outputs. The ground on the hard disk can be lifted by isolating this one leg. This should correct hard disk audio noise at the outputs. Units produced between December 1987 and May 1988 have experienced power-related problems due to improper contact at the power supply and motherboard connections. Single-wipe connections were used in both of these positions. These single-wipe connectors have a tendency to lose their contact due to poor positioning. Poor contact can cause intermittent lockups, no boots, and possible hard disk crashes. We have replaced the single wipe with the Trifecon connector. This connector surrounds the post on all three sides, making a secure fit. Units produced between December 1987 and August 1988 may have leaning SIM sockets on the microcontroller boards. These leaners, as we call them, were a result of our supplier cutting double SIM sockets in half. When the double connector is cut in half, the standoffs to the connector are only on one side, causing the socket to lean. We have investigated these leaners causing intermittent memory problems. The conclusion was that the leaners are just as good as the straight or single SIM sockets. The problem with the leaner sockets is that the proper insertion of the SIM is difficult. Intermittent memory problems are due to improper insertion or contamination. We have discontinued using the leaners due to the aesthetics and possibility that they may have caused intermittent memory problems, and now only use these straight or single sockets. E3s manufactured between December 1987 and April of 1988 have experienced problems with the pop at the beginning and or the end of a sample. The problem has been corrected by decoupling the DBX amplifiers from the Murata filters. We will cover this modification a little later in the video. Units manufactured between December 1987 and April 1988 may lock up or crash when receiving MIDI in data. This is due to an improper reset value on the clock timer located in IC30 on the CPU board. There are two fixes for this problem. The first we call the cap mod. A 2200 or 1800 picofarad capacitor is placed between pin 30 and pin 8 on the backside of IC30. The second way is used in current manufacturing and will work with version 1.21 software or greater. Instead of using the capacitor, the line is run through a buffer. Pin 8 of IC30 is jumpered to pin 13 of IC7. The trace at pin 14, IC1, is then cut at the pin. Before performing any of the trims to the E3, be sure to let it warm up for at least 1 hour. This will ensure that the E3's condition is typical of its actual use and will allow the temperature of the components to stabilize. The first trim should be the plus 5 volt line on the power supply. This can be accomplished while the E3 is open, in the service position, and on the technician's bench. Use a digital multimeter only, as accuracy down to 1/100th of a volt is necessary. Measurements of 5.02 are taken at the Molex connector on the front of the power supply. The wheel and slider calibrations must be correct before starting the analog trims to the E3. Make sure these are correct by going into the recalibration routines found by hitting Master, Special 8, Recalibration 3. Recalibration can be performed on all the real-time controllers in this menu. The filter trims are accomplished in software. The E3 doesn't even have to be opened in order to perform this. You should have a copy of the E3 service manual around for reference. You will also need a copy of the E3 Universal Sound Test Disc, an oscilloscope, headphones, or an amplifier and speakers. First, boot the E3 from the internal hard disk and let it warm up for at least 1 hour. Load the E3 Universal Sound Test Disc. Select preset 16, which is a 500 Hz sine wave at 100% modulation. Connect the oscilloscope to the mono mix-out jack using an appropriate adapter. Make sure the master volume control of the E3 is at maximum. The first 16 keys of the keyboard are assigned to the 16 individual channels. Play each one separately while observing the oscilloscope. You should see very clean sine waves of at least 1 volt peak to peak. If the E3 has had the hot output modification, you will probably see about 4 volts peak to peak. If any of the individual channels are far below this, suspect a bad Curtis filter chip. Now change to preset 28. This is a 500 Hz sine wave at 60% modulation. The E3 amplitude trims are done at this point to improve the VCA response linearity over an entire volume range. Next, we will enter the diagnostics module. On version 2.0 software or greater, press Master, 8, and 0. You will see the message, Enter Magic Code. Enter 1, 3, 5, and then 8. You will now be in the diagnostics menu. Next, enter the analog trims submodule by pressing 5, and then 1 for manual trims. You will see a window of many numbers representing the trim values for frequency cutoff, Q, and amplitude or volume. If you are trimming an E3 that has never been trimmed before, you will see all 99s. Otherwise, you will see a variety of numbers. If you are attempting to do a spot trim to tweak a few channels, you can cursor to the appropriate location and change the individual value as necessary. It is highly recommended that you do a full retrim when possible, especially if it has had any parts change that affect more than one channel, such as an SSM 2300, which supplies control voltages for all the channels on a board. This is done by setting all the values to 99 in the window. For this demonstration, we will start from a system of all 99s. The current preset should still be at the channel assigned 500 Hz sine wave at 60% modulation. The scope setting should be on 0.5 volts per division vertical and 1 millisecond per division horizontal. Play each individual channel and find the one which displays the lowest amplitude. Adjust the vertical position on your scope so when playing this channel, the sine wave is riding the bottom line of the scope window. All other channels will then go outside of the window. Put the blinking cursor under the 99 for channel 1 amplitude by using the cursor and page buttons. Now hold down the C1 key and press the decrement button until its sine wave is riding on the bottom line of the scope window, like the one before. Go through each channel using the cursor and decrement buttons until all amplitudes are as close as possible. When you have finished this, hit the Enter button. The window will ask if you want to save these trim values. Press the Yes button. Now press the Master button to exit the module and select Preset 13 Resonance. This is a channel assigned silent sample where we will do a rough setting of the FC and Q values. Go back to the Diagnostics menu and then Analog Trims. With all the Q and FC values at 99, you will notice that each of the channels will be playing a high-pitched sound, which is caused by the filters going into oscillation because of their extremely high Q values. Find the channel with the lowest pitched sound. This will be the reference channel. Using the page and cursor buttons, go to the FC value for the channel and set it to 95 with the decrement button. This will give us some room to fine-tune this channel if necessary later on. Select each of the other channels and bring down their FC value until they oscillate at approximately the same pitch as the reference channel. This is a good rough setting of the FC balance between channels. Next, go to the Q line and lower the values until each channel just drops out of oscillation. This will be a good rough trim of the relative balance of Q between channels. Hit the Enter button and press the Yes button to save these trims. Press the Master button to exit the module. To fine-tune the FC value, enter preset 10, which is a sample of white noise, and then go back to the manual trim window. Adjust the individual FC values by ear to match them as close as possible. Then exit the window and go to preset 11, which is white noise with a medium amount of Q. Go back to the manual trim window and fine-tune the FC and Q with this sound. You will find that it is impossible to get the match perfect between the no Q and medium Q sounds. This is a limit of the analog components. Don't worry too much about it though, because the differences are barely audible in real-life musical situations. It is a matter of personal preference whether you adjust the best balance with or without Q, and may be determined by knowing the user's preference. After finishing the filter trims, copy the software and calibrations that are now stored on the hard disk to a floppy disk as a backup. This is accomplished by using Copy Software Routine in the Disk Utilities module. Before we begin the ADC board trims, let's look at the ADC board and identify the differences you might find in them. Originally, the boards looked like this. Notice the lack of capacitors in the C8 and C19 locations, and the absence of the resistors in the R11 and R17 locations. Also note that the 6 trim pots are laying down against the board. The next board shows ECO number 1025 having been performed. Note the 4 new capacitors and the additional resistors. Also note that the trim pots have been replaced so that they stand perpendicular to the board. They have been slightly twisted and the DBX chips are slightly bent over, which will allow trimming to be done while the board is installed in the card cage. Also note the group of cuts and jumps on the solder side of the board. No further modifications are necessary to this board. This last board is a view after ECO 1118 has been performed. Note the double capacitors attached to the Murata filters and the additional resistors that may be attached either on the top or the bottom of the board. Again, the trim pots are standing up straight and slightly twisted to allow for easy access while the board is in the cage. Once you have determined the proper modifications have been done to the board, you can start with the trimming procedures. Set the sample input slider to -6 dB by entering the sample gain check. This is done by entering diagnostics and then choose 7, sample gain check. Use a signal generator and put a 1 kHz 2.82 volt peak-to-peak sine wave into the left sample input. This can be measured at the right side of R8 on the analog jack board, which is not stuffed. It can also be measured with a Y-type splitter cord. Then press enter. Set the sample input slider so the VU reads -6 dB between the A and I in gain. To avoid having to repeat this procedure, take a pencil and lightly mark the position of the sample input slider on the front panel. Remove the signal generator from the sample input. Now re-enter the diagnostics menu and choose number 6, ADC trims. Make sure the sample input slider is still set at -6 dB. Press the enter button for half a second. The computer is calculating conversions hard and fast here, so whenever you press enter in this mode, you must hold it for at least 1/2 second. The DC offset trim pots are located approximately in the middle of the ADC board. Adjust RT3, the one in the rear, for minimum DC offset. Next, adjust the front trim pot to minimize the right DC offset. Press enter. Connect the mono mix to the left sample input. Press enter. You now see a bouncing bar graph. While looking at the bar graph, adjust RT4 located at the front right of the ADC board for the most stable setting. Next, adjust the left harmonic trim pot located at RT1 at the back left of the ADC board. Now adjust the trim pot for minimum overall distortion. The bar should drop below halfway. Press enter. Move the cable from the left sample input to the right sample input. Press enter. Adjust RT6 located in the back right of the ADC board for its most stable setting. Next, adjust the right harmonic trim pot located at RT2 at the front left of the ADC board. Now adjust the trim pot for minimum overall distortion. The bar should also drop below halfway. Press enter. You now will be back in the diagnostics menu. This trim is now repeated one more time to assure minimum DC offset levels.
This man is not juggling. He is merely explaining to a juggler how to operate his Emulator 3. If you have any questions regarding the emulator, call him Mr. Signal 408-438-1921 or send a fax 408-438-8612. This man is not juggling.
Troubleshooting the E3 can be a breeze or it can be an overwhelming experience. The important thing to know is what to look for if a problem occurs. In this troubleshooting section, we will cover basic problems encountered and recommend a solution. The recommended solutions are to point you in the right direction to solve the problem and may not be the fix in every situation. No power. Check the AC fuses located to the rear of the E3. If they are blown, there is a reason, so before you install new ones, check the following. The power supply varistor located at VR1. The power supply fuse. Blown decoupling capacitors on PCBs. A bad DC wire harness. When the supply is working, you should be able to read plus 12 volts on the orange wire, digital ground on the green wire, plus 15 on the red wire, analog ground on the blue wire, minus 15 on the black wire, and plus 5 on the yellow wires. If the E3 won't boot up on the internal hard disk, searches SCSI continuously, or displays a SCSI hardware error, first try and boot from the floppy disk. If you can, try and access the hard disk. If you can access the hard disk, erase the software from the hard disk. Copy software from the floppy to the hard disk. The software may be corrupted on the hard disk. If you do not have the customer system disk, the E3 will need to be recalibrated and retrimmed. If you cannot access the hard disk, check the power at the hard disk. It should be no less than 4.7 volts. Also check the CPU to hard disk cable for continuity. Try and reformat the hard disk. If you cannot, the hard disk heads may have crashed and a replacement hard disk is required. Check the SCSI controller chip and surrounding logic. If you cannot boot from the floppy disk drive or the hard disk, carefully reseat the SIM chips in the sockets on the microcontroller board. Check for adequate DC voltages, and check the CPU reset and timing circuits. If the E3 appears to boot, but the message "Can't load system" appears in the display, chances are that there is a memory problem. Remove the SIMs, clean the fingers, and reseat them in their sockets on the microcontroller board. Be very careful when handling the SIMs because they are very static sensitive. If this does not solve the problem, check the 8 latches carrying data and address lines to and from the SIMs. Remove the PCBs and clean the gold fingers with a pencil eraser. The eraser will polish the gold, removing any contamination on the upper layer. SCSI media error. This is possibly caused by intermittent power to the hard disk due to a bad DC harness or poor AC line voltage. This error may be corrected by changing to the Trificon wire harness or by using the read-write reassign in diagnostics to overwrite the hard disk bad block. Intermittent memory crash. Make sure that the DC harness is making secure contact. Reseat the SIM chips in the sockets and check for contamination on the board edge connectors. Also check for possible bad wash on CPU chip IC17 on the CPU board with date code 8730. Clean the pins of this IC by using an eraser. Sample DC thump. If a thump occurs at the beginning or end of a sample, the ADC DC offset will need to be adjusted. This can be accomplished by trimming the ADC board. Stereo outputs not working. If the individual outputs are functioning and the stereo outputs are not, or you hear a chattering sound, the stereo output relay is malfunctioning or not getting the proper voltage. A measurement of 4.9 volts should be read at IC3, pin 8 on the analog jack board. If voltage is not present, check the continuity of the A cable coming from the lower output board. If the voltage at IC3, pin 8 is low, the 5-volt line should be adjusted at the supply and measured at IC3 for 4.92 volts. Individual channels not working. If an individual channel is not working, check the output board to analog jack cables. D cable carries channels 1 through 4. C cable carries channels 5 through 8. B cable carries channels 9 through 12, An A cable carries channels 13 through 16. A bad channel may be caused by poor contact or contamination of these cables. Another channel symptom is one of losing either the left or right outputs. This is usually caused by contamination of the channel output jack or intermittent cables from the output boards to the analog jack board. These jacks are self-wiping, and exercising the faulty jack with a 1/4-inch plug will wipe the contamination clean. Digital noise through audio outputs while loading a hard disk bank. If digital audio noise is heard through the outputs while loading a bank, one of the SSM 2300 sample and holds is drifting. Check IC44 for the amplitude sample and hold, IC43 the Q sample and hold, and ICs 40 and 41 for FC controllers. IC40 and 41 can cause slight distortion or buzzing sounds in the background of the audio outputs. Display problems. There are 3 types of display problems. No backlight with text on the screen, no text on the screen with backlight, and no screen at all. No backlight with text on the screen can be due to this high voltage transformer malfunctioning. Approximately 100 volts of AC should be measured across these 2 terminals. It could also be due to the LCD malfunctioning. If there's no text with a backlight only, the CPU has crashed before starting the program. This could be caused by a bad hard disk or no power to the hard disk. It could also be a result of malfunctioning latches to the memory. Check ICs 14, 15, 20, and 21 on the CPU board at pin 1 for output enable. If there's no text or backlight, the front panel is not getting power. Check the voltage at the CPU board. You may have a bad ribbon cable between the CPU board and the front panel. If there's no voltage at the CPU, trace the problem back to the power supply. No boot with boxes in the display. If the E3 powers up but has boxes in the display, chances are one of the interface ICs to the front panel has blown. These interfaces are ICs 26 and IC40 and are very static sensitive. We hope that this video has been beneficial to you, our service support network, in helping to clearly identify failures that may occur in the E3. We feel that today's production Emulator 3s are of the utmost quality and would like to assure the same to our existing customers. If you should have any further questions, feel free to call us at 408-438-1921 or use our fax 408-438-8612. Thank you for taking the time to watch this video.
Excuse me.
And your loyal devotion to EMU systems.
It was working fine. I don't know. And then, is this covered in warranty?